Welcome to Organic Chemistry 1. In these videos, I try to go over the important parts of each chapter for you based on Smith book. But before we start, let me tell you, just working on the videos and the study guides based on the videos might not be enough. You need your ebook, working on the smart book as well, and the end of the chapter problems for sure to make sure you succeed in this course. So again, I will be working on the most important parts, the topics of each chapter with some of the practices that you have in the study guides. So let's start with the study guide number 1, or let's say chapter 1, let me call them chapter 1. About the structure and bonding. You all have had an introduction of organic chemistry in your general chemistry 2. So the first 3 pages of this study guide are about what you had in general chemistry 1 and 2. And let me tell you, a lot of portions of the material you have in organic 1 are based on what you had in general chem 1 and 2. So don't think that because you are in organic class you are not dealing with any of the concepts of general chemistry. No, that's not true. So you will see that we will go back to general 1 and 2. That's why they are the prerequisites for your organic chemistry 1. Anyway, let's start. I try to break the materials in different videos so you won't be tired and you have the time to pause and practice. The first 3 chapters I told you, it's like a short quiz about what the atoms and the electrons and neutrons and protons, and working on some famous medicines, like drawing their structure. But what I'm going to start with is the concept of formal charge. If you remember, you had it in general chemistry also. I need to adjust the video. Okay, the formal charge. For formal charge, first of all, let's find out the description. Formal charge is a hypothetical charge. Means it doesn't exist. It's something hypothetical. We will have to determine the formal charge to be able to judge on Lewis structures of the molecules. So there are different formulas how to calculate the formal charge. What I think is the easiest is number of valence electrons in free atom minus lines plus dots. And if you notice, lines are bonding electrons and dots are non-bonding electrons, right? So instead of like saying half of the bonding electrons minus non-bonding electrons on all of these, I just use it as lines plus dots, but you'll have it on page 4 of your study guide as number of valence electrons minus number of unshared electrons minus half of number of shared electrons. Feel free to use whichever sticks to your mind better. Anyway, let's go to the table on the bottom of page 4 and determine some formal charges. Well, how to apply this formula on finding the formal charge. For example, if a carbon atom has 4 single bonds, let's determine what would be the formal charge. The valence electrons, the number of valence electrons in free atom is the same as group number, or let's say last digit in group number. Carbon belongs to group 4 or 14, so the number of valence electrons in free carbon is 4 minus, how many lines do you see around this carbon? I'm sure you'll say 4. Do we see any dots? No, so it's 0. So the formal charge for carbon with 4 single bonds is always 0. Let's go to the second one. I do it for carbon. I'm sure you can continue with nitrogen and oxygen. For carbon, with only 3 single bonds. So 4, the number of valence electrons in free atom is the same. How many lines do you see? Instead of 4, now we have 3. And how many dots? 0. So such a carbon will have a formal charge of +1. So you will see a +1 or a +1 inside a circle. And for the last carbon that you have 3 single bonds and a non-bonding electron, you have 4 minus 3 lines plus 2 dots, so you have extra electrons, so you will have -1. All right, so that's how you determine the formal charge on an atom. I told you, I work on some of the questions you have on your study guide, based on the chapters. Let's try to draw. The first thing in organic chemistry, just like the general chemistry, is how to know how to draw the Lewis structures. Like for example, if we have C2H6O, we want to draw it, we will need to make sure that, as you remember from general chemistry 2, that we must have 4 bonds around each carbon, or let's say 8 electrons. We must have complete octet. So we have 2 carbons. Let's connect these 2 carbons first. Let's put 3 other bonds to complete the octet on this carbon, and they're all hydrogens. We need 4 more bonds around the second carbon. We will have 3 more hydrogens and 1 oxygen. So we cannot say 3 more hydrogens, but where do you want to put the oxygen? The only way to connect the oxygen is to put an OH. And later on, you will learn that this is called an alcohol. You had a chance to learn some functional groups in general chemistry too. So anyway, this is how you draw a Lewis structure for an organic compound. Maybe not the complete, accurately Lewis structure, but based on the angles, but this is called the line bond structure. So this is how you normally show the Lewis structures for each organic compound. I'm going towards the bottom of page 5. Let's try, and I'm telling you, at the beginning of this journey of organic chemistry is about writing and practicing and practicing. So it's not something just you can get by watching the videos or just reading online. So you have to have enough practice by drawing, making mistake, and learning. Let's go to the end of page 5. Draw Lewis structures for each molecular formula. I believe B is a good choice. We are working on page 5. B, drawing the Lewis structure of C3H8O. So we have total of 3 carbons, 8 hydrogens, and 1 oxygen. So one of the compounds, these are all carbons with complete octet, right? Five, 6, 7, and as we said in the previous example, we can have an OH. Now try to move your OH to have OH on the second carbon, and leave the rest of the hydrogens on the last carbon. In each case, you must have 3 carbons, 8 hydrogens, and 1 oxygen atom. Okay? Now you might say, okay, we had OH on the first carbon from right side. Then on the second one, how come we do not put it on the next one? The next one, if you put the OH on here, it looks like you have it here, but you flipped it. So wait until you learn how to name. And you already know how to name from the general too, but you don't know how to name the alcohols. Anyways, so when we have the OH on the first and the second carbon, we have two different structures. And another structure, if you think of, is this carbon oxygen single bond. And do I have 8 hydrogens? Yes. 3 here, 3 here, and 2 here. So these are the 3 possible isomers for this compound. Don't forget to practice on the rest, on A and C. Now, you might ask, what is the point of formal charge? You said it's hypothetical, but as I told you, we need to sometimes decide between different Lewis structures which one is more correct, or which one is the only correct Lewis structure. So that's how we use the formal charges. Let's talk about resonance at this point. It's a small board, I have to make some room each time. All right, so let's say we talk about resonance. Do you remember resonance from General Chemistry 1? Resonance structures show the flow of electrons in different Lewis structures. Okay, so for having resonance structure, not necessarily we have this resonance structures for every single Lewis structure that we draw. We must have the conditions. There are 3 main conditions that it makes it possible to have resonance structures. So let's work on the first possibility. For each resonance structure, for having the resonance structures, we must have a source of electrons, and target for electrons, target for those electrons. So you can imagine that flow of electrons is going to be from source towards target. So now we are going to study 3 conditions of, or let's say 3 types of source and target. The first one is that when source is a double bond, and the target is a positively charged carbon, or what we call it, cation. We have the example here. So you see, this is going to be your source, the double bond. It can be carbon-carbon double bond or carbon-oxygen double bond, doesn't matter. So source, and we have a target. So electrons move from source to a target. Don't forget that electrons cannot jump more than 1 carbon. Electrons are short and they cannot jump. Between the resonance structures, again, if you remember from General Chemistry 1, you have a two-way arrow, two-sided arrow. Now, you showed the flow of electron. Let's determine the second resonance structure. You showed that the electrons from double bond moved between the 2 carbons. So between carbon and oxygen, there will be only a single bond. The number of electrons didn't change. None of these non-bonding electrons moved. And these electrons changed to the double bond between the 2 carbons. Now, Nothing happened to these two. Now, let's determine the formal charges. If you calculate the formal charges for this oxygen, you will find out that we have 6 minus 4 plus 5, so electrons moved away from this oxygen. So the formal charge from that formula is positive 1. You have to put a positive charge on oxygen. Means that electrons moved away from oxygen. Between the two carbons, when you calculate the formal charges on each carbon, you have 4 for the free carbon plus lines minus dots. 4 lines minus 0. There is no formal charge on this carbon, and the same for this carbon. Just use the formula for formal charge. So it looks like positive charge moved away from carbon on top of oxygen. Do you remember I told you resonance structures and formal charges are related to each other? Formal charges are used to decide between the major Lewis structure. Now you would ask me which one of these is the major, or let's say more stable resonance structure. There are some rules for formal charge. First of all, no formal charge, 0 formal charge on the atoms is the best. But is this the case here? No. On each of these resonance structures, you see a positive charge. So we go to the second postulate. The second postulate about formal charges says if the atoms are charged, the compound, the structure is more stable, that has the positive charge on less electronegative element. So first of all, I told you about formal charge. 0 formal charge is better, no formal charge. And the second rule is positive charge on less electronegative element. So we need to have a quick reminder about electronegativity. What was the description of electronegativity? Tendency of atoms to pull the electrons, the shared electrons in the covalent bonds. And in organic chemistry, we're talking about covalent bonds, whether polar or non-polar. So, electronegative element wants to pull electrons. So it makes sense that it always holds the more negative charge. So if oxygen is more electronegative than carbon, because electronegativity, electronegativity increases left to right across the period, and also from bottom to top of the group. So between carbon and oxygen, oxygen is more electronegative. If it is more electronegative, it tends to have more negative charge on it, not a positive charge. So between these two, a more stable Lewis structure is the first one with positive charge on carbon, which is less electronegative element. Don't forget these two rules to be able to determine the major Lewis structures. All right. Now we are ready to go to the second condition of source and target. Ready? I will work on the same place, just erase. Okay, the second one is very rarely happening when the source is, oops, I don't know what happened to my marker. Let's dismiss it. Okay. Double bond is your source again, and target is a radical. What is a radical? Is an atom with a single electron, not a lone pair. It's just one single electron. So let's work on what we have on page 6. All right. So we say in a covalent bond, the two electrons are shared, right? Can I draw this covalent bond as two dots, two electrons connected? Of course, yes. So what does this carbon need? Just one single electron to complete its octet, because now it has 1, 2, 3, 4, 5, 6, and 7. So what happens is that one electron, and be careful, when you are sharing electron, just one single electron, instead of having a complete arrow, you just show it as a hook. That's the only time that you don't show the complete arrow. So if it was complete arrow, it was a complete pair. Now, because it's not a complete arrow, so it shows that it's just one single electron. The same here, okay? So you are sharing the two single electrons with two hooks. Now put the resonance symbol. What happened here between these two carbons? There should be a double bond formed, right? And none of the other bonds changed. So if you calculate the formal charge on this carbon, it would be 0. Basically, whenever you see 4 single bonds around the carbon, its formal charge is 0. The same here, but on this carbon, you left one single electron, correct? So you leave this on the single. So it looks like one electron moved to this side. Now, between these two, what is the priority? No priority. They're equal because they have equal stability, because there is one single electron on each of these carbons. Okay? Ready for the third one? I'm sorry, that was the second one, right? So let's work on the third one here. If, or you can see better. The third one is the first and the third one are the most common conditions for source and target. Non-bonding electron pair, the whole pair, the electron pair acts as source, and your target is another double bond. Another bond which is double bonded atom. Like what? Like we have so source is this, target is this. Electrons move from source to this bond. They do not jump too much, right? And then this double bond opens to keep the octet complete on this carbon. Otherwise, you will have 5 bonds and 10 electrons instead of 8, because you will have 1, 2, because the double bond is about to form. 5, 6, 1, 2, 3, 4, and 5. So the other Lewis structure is going to be this bond opens, so it's 1, 2, 3, 4. This bond opens to an extra lone pair. Here you have a double bond formed because of what? Because of these 2 electrons. So you have 1, 2, 3, 4. Now it's time to calculate their formal charges. For carbon and for this oxygen, formal charges are 0. The only atom with a negative formal charge is going to be this. Now, if you want to decide between these 2 Lewis structures, which one is more stable? Do we have 0 formal charges? No, we have a formal charge. But do we have a positive charge? No. And negative charge is on oxygens in both of them. So we have equal resonance structures. They both have the same stability. So 50-50. I hope it was clear. So what we have to be very careful is 3 things. We are not moving the atoms. As you saw, we just moved the electrons. We move away the electrons just like this double bond to avoid violating the octet rule. And we do not change the overall charge of the molecule. What is the overall charge of molecule here? -1, right? Because of this -1 here. And what is the overall charge here? -1. So don't forget these 3 rules. Do not move the atoms, just move the electrons. If you are violating the octet, it means that you need to move a bond. And the third is that the overall charge on all of the resonance structures must be the same. If it is 0, 0. If it is positive or negative, it must be the same. The overall, okay? The overall charge must be the same. Okay, so let's move on to the big table on page 7 you have. And let's determine the first resonance structure. Okay, the arrows are shown. Seems like this is the flow of electrons. Those that we mentioned, there are 3 main sources and targets. You can have other source and targets. So first of all, you need to make sure you put the resonance sign, and then hydrogens remain intact. There is no double bond here anymore, so you put a single bond. Double bond will be formed between these 2 carbons. And you see, because we don't want to violate the octet on this carbon, so the electrons should move away. I'm sorry, this is a carbon in here. We have 3 non-bonding pairs because this double bond changes to a new non-bonding pair. Okay, when you determine the formal charges, you will find out that you have a negative charge on that oxygen. How about this carbon? It has 3 single bonds. When you plug it into the formula for formal charge, you will have a positive. So between these 2, which one you think is the more stable compound? First rule, the one without the formal charge is the major product. And you see that the overall charge, what is the overall charge on this molecule? I'm sure you don't see any charges, you would say 0. And what is the overall charge on this? A +1, right? -1, right? 0. So we kept the the overall charge the same. So that's a check to your work. And I'm sure you can do the second and the third. Let's take care of the one with a circular structure. I'm sure you see more than 1 resonance arrow and you get confused a little bit maybe. So let's work on that. So why do we have more than 1 resonance structure? Because you have more than 1 double bond. You see that you can move the electrons here because you want to keep the octet complete on this carbon because they're all carbon. We will learn how to draw all of these structures. Do not rush. Then electrons, I told you, they are little tiny electrons. They cannot jump too much, so they just go over the second carbon, the other carbon. So the first structure you will have is, nothing happened to these 2 double bonds, right? This double bond moved over this carbon, right? And one of these electron pairs changed to a double bond. So the movement of electrons just happen on this side. You need to determine the formal charges. If you calculate the formal charge, you will see there is a positive charge on oxygen. 6 minus 3 plus 2 is positive 1. That makes sense because electrons moved away. On this carbon, you have, don't forget you have a hydrogen here. So you have 3 plus 2, 4 minus 3 plus 2. There is a -1 charge. So let me eliminate hydrogen. And then because you still have more double bonds, the electrons keep moving around the circle, around the loop. So you have the same thing. Electrons go from source to target, source to target. Okay? I put these because I already know how to calculate the formal charges. The formal charge is the same. Nothing happened between these two on the oxygens. The only thing you need to calculate is the carbon, the formal charge on carbon, and it's obvious because the electrons move. But always calculate the formal charge from the formula. One more. We have one more double bond here. Don't have any more space over there, so let me draw it here. So we have a double bond here because of this movement of these electrons. The negative charge here now, nothing happened to oxygen. And this. And then finally, if we move these electrons over this bond and electrons go back to oxygen, we will go back to our first structure. So the more bonds, double bonds you have, and they must have one single bond away from each other, then you will have more resonance structures. Those of you who need to take organic chemistry too, you will learn about conjugated systems, and you will learn that this is a very good and stable conjugated system. And there is there a difference between these different resonance structures? Yes. This one has no formal charge, so this is the most stable, because for the rest of them, the electronegative element has a positive charge, which it doesn't like. All right, so let's see what else we have here. Okay, we are catching some mistakes in the molecules. We are going to find out, not the mistakes, but let's say when I told you the resonance, I told you that not necessarily every Lewis structure has a resonance. So let's see, there are two structures given, why they don't have resonance structures. We said for each resonance structure, we must have a source, we must have a target. So let's check if we have both of them. If you look at this compound, you see there is a source, right? But do you see a target? Do you see a positive charge? Do you see a double bond? Do you see a radical? No. So there is no target here. So where do the electrons flow to? The second one, you have this. Seems like we have a target, we have a positive charge, but where is the source? Where do the electrons come from? So there is no source and there is no resonance structure. So the conclusion is that in order to have the resonance structure, we definitely must have both source and target. You need to decide between some compounds are given here. I told you I'm going to try not to work on every single practice, but seems like the first study guide I might need to work on more. This is compound A. This is compound B. This is compound C. And this is compound D. So So we are supposed to find the relation between these compounds, A and B, A and C, A and D, and B and D. We need to find out if they are isomers, resonance structures, or neither. Do you remember from general chemistry 2 what are the isomers? Isomers, there are different types of isomers first of all. We will learn different types, but we are talking about structural at this point. Structural, or another name for it is constitutional. I told you, we will learn more about the different types of isomers. But for now, we're talking about constitutional or structural isomers. They are they're compounds with the same formula, different arrangement of atoms. Okay, so between let me tell you. Okay, let's start determining the relationship between these compounds. We will talk about isomers. So between A and B, what you see? Seems like electrons moved away from oxygen and this bond opens. So A and B are resonance structures. Same molecule, different flow of electrons, resonance structures. A and C. A and C. I see totally different, no, not totally different. A and C are isomers, right? So we have 1, 2, 3, 4. No, you see the formula here is how many carbons? 2. 2 carbons, right? Compound A. How many hydrogens? 4. And how many oxygens? 2. For C, how many carbons? 2. How many hydrogens? 5. 3, 4, 5. And 2. So since the compounds don't have the same molecular formula, so they are totally different compounds. You just say neither. They are not isomers, they are not resonance structures. Between A and D, what you see between A and D, let's see, the formula for D is C2. How many hydrogens? 1, 2, 3, 4. And how many oxygens? 2. But is it, so far they have the same formula, right? But is the arrangement is the same? No. So they are isomers. Structural isomers. Different. The same formula, different arrangement of atoms. And between B and D, again, I see, let's determine the formula for B. 2 carbons, 1, 2, 3, 4, and 2, O2. So between B and D, you have different arrangements, right? So these are another isomers. Okay. All right. I hope you had a better idea about the difference between isomer and just resonance structures. So resonance structures, they have the same formula, but the flow of electron is different. But the isomers, they have the same formula but different arrangement. Okay, I'm sure you can work on the flow of electrons, the bottom of this page, and before we finish this video, let's work a little bit more on determining the major Lewis structure on page 9. allow me to skip drawing the hydrogens to save time. What are we supposed to do here to show the flow of electrons and find the major product or determine if they are equal? So what happened during this transition is we have this and this. So seems like electrons moved from carbon over this bond and the bond open to keep the octet complete. Which one of these is major? Remember the formal charge rules. The compound with 0 formal charge is preferred, so this is the major product. Let's move to the last one. I'm sure you can do the second one. You can pause the video, do the second one, and then see what I'm working on. Good thing about online learning is you can pause it anytime you want. Okay, let's determine the flow of electrons. Seems like there was not a double bond here, so now it's going to be formed. The double bond fades here and there will be a single bond. Now let's determine the stability of these two. Which one is more major? In each of them you see there is a positive charge on nitrogen and each of these oxygens will have a negative charge. So it seems like we have equal stability of resonance structures. Okay, work on the next practice. Now you deserve a break after a 40-minute organic chemistry video. Work on this part until the next video coming out.